All right, to start off this chapter, let's take a look at nuclear energy. So, trying to use fossil fuels is not going to be a long-term sustainable thing. We've been using them for a long time, but they are finite. And as we've seen so far, fossil fuels are not exactly the best thing for our environment. So there are other types of energy out there. We have nuclear energy, we have wind energy, and we have other types of renewable energy like solar and things like that. So when we look at these nuclear energy right now, we've got some incentives trying to get some emphasis going on nuclear energy. Okay, so when we look at nuclear energy, it's this red line down here. So still, fossil fuels are huge compared to other types of energy. So what can we do to try to boost up other types of energy? Okay. Now, when we look at nuclear energy, we want to understand that there's some different things that happen. So in a non-nuclear reaction, all we do is rearrange the way atoms are connected. We don't actually change the identity of the atoms themselves. However, in a nuclear reaction, there's different things occurring, and we actually do change the identity of the elements themselves. In a regular non-nuclear reaction, we're just reacting with the electrons, usually the valence electrons. What's in the nucleus, the protons and the neutrons, those are not involved. But in a nuclear reaction, protons and neutrons are involved, which is how we end up changing the identity of the element. So as long as we keep the number of protons the same, the identity of the element stays the same. But if we start messing with the number of protons, now we start messing with the identity of the element itself, because the number of protons is what sets the identity of the element. Non-nuclear reactions have very small energy changes. Nuclear reactions have much, much, much larger energy changes. Non-nuclear reactions, we look at temperature, concentration, if a catalyst is there, etc. For a nuclear reaction, we look at the number of nuclei involved, but the rest of that doesn't matter the same way. Okay. When we look at nuclear reactions, we have radioactive decay. So there are some elements that are not stable, and so they are radioactive naturally, so they will undergo some type of decay. We can predict the type of decay actually based on where they are on the periodic table. So we have this thing called the band of nuclear stability, where based on the region of the periodic table an element is, there's a certain ratio of protons to neutrons that provides a stable element. So early on the periodic table, it's about a 1-to-1 ratio. Then we get about a 1 to 1.25. Then we get up to a 1 to 1.5 ratio. So as we get to heavier and heavier elements, we need more neutrons to help kind of keep things together. And so if we're out of ratio, an element will undergo a decay pattern to get back into whatever ratio works to give it something stable. We also get nuclear bombardment, where, and this is where we force nuclear reactions to happen, where we forcibly send something at an element and we collide it and we wait to see what happens. Sometimes we're doing it purposefully, other times we're doing it to say, hey, what happens if I shoot, an alpha particle at this element? What can occur? Okay. To understand nuclear reactions, we do need to understand atomic notation. So we have these types of symbols here where we've got the symbol of the element, we have a mass number, and we have an atomic number. Now, it's important to note what's on the periodic table. We have the symbols of elements, we have the atomic number of elements, but what is on there is not typically a mass number. What's on there is what is an average ratio. We've got this weighted average of all the different isotopes. So isotopes are individual atoms that differ in the number of neutrons, but not the number of protons. So I could have, say, a carbon atom where I have 6 protons and 6 neutrons, or a carbon atom where I have 6 protons and 7 neutrons, or a carbon atom where I have 6 protons and 8 neutrons. They're all carbon atoms because I still have 6 protons, but I have a different number of neutrons for each one of those isotopes. And so what ends up happening is they're not all equal. I don't have a 33.33%, 33.33%, 33.33% distribution of all three of the naturally occurring isotopes. Each isotope has its own naturally occurring abundance. So for carbon-12, that's 6 protons and 6 neutrons. We've got a natural abundance there of like 99% practically. So it's the vast majority of all carbon is carbon-12, which is why the mass reported on the periodic table is 12.01, because most of the carbon is carbon-12. When you get to something like silver, it's like 107 point, I think 45. I could look behind me, but I have my glasses on. I can't see far with my glasses on. But it's like 107.45 or something, because there's silver 107 and silver 109. Silver 107 is present in a slightly larger percentage than silver 109 is. So we get a little bit more weight toward the silver 107. So to get that mass number, all we do is we add together the protons and the neutrons. So like if I had carbon-12, I'd have carbon, oh, okay. My iPad's being disrupted, but let's see here. If I had carbon-12, I'd have, write it like that. If I had carbon-13, I'd write it like that. If I had carbon-14, I'd write it like that. Okay? So I point this out because we need to understand this atomic notation, because we need it in order to write nuclear reactions. So when we write a standard chemical reaction, we don't really care about the mass number or the atomic number. All we care about is the identity of each element and balancing the number of atoms on each side. With a nuclear reaction, what we're trying to understand is, what are we converting things into? What type of nuclear process is occurring? And so we have to make sure that it's not the coefficients in front of each atom that add up this time, okay? So we're gonna have different atoms on each side of our reaction. What we care about is making sure that the total count on the mass number is the same and the total count on the atomic number is the same, okay? So let's take a look at this, okay? So here is a sample reaction. What ends up happening is I have this thorium-232. So thorium has an atomic number of 90. Our mass number here is 232. Now, what's happening here is we are undergoing something called alpha decay. Alpha decay is the emission of a helium nucleus. So here is our helium. So we want to know what we put there. X and Y, what are they? So I have, on this side of the equation, I have this 232 as my mass number. So what I need to make sure is I need to make sure that my mass numbers add up to 232 on both sides. So for my helium, I already have this number 4 here. So I'm going to take 232 minus 4, and that's where I got that 228 from. Okay? Now I have down here, I have this 90. Okay? Now that 90, that's my atomic number. I still have to make sure both sides of my equation add up to 90. So I already have 2 on my helium. So 90 minus 2 would be 88. So I look on the periodic table and I figure out what element has atomic number 88. And so what I get is a full nuclear equation that looks like this. All right, so there's my nuclear equation. So 228 plus 4 gives me that 232. 88 plus 2 gives me 90, okay? And so this is how we balance atomic, or nuclear reactions, not atomic. This is how we balance nuclear reactions, okay? So it's, again, it's a little different than when we balanced standard chemical equations. Now, instead of making sure I have the same number of each element on both sides of my equation, I'm trying to make sure that my mass numbers add up and my atomic numbers add up. Because what's happening is I'm taking an element and something else is happening to it. We're becoming a different element through a nuclear process. We have all sorts of types of nuclear decay. We've got alpha particles, beta particles, gamma rays, positron, neutron, protons. And so we get some changes based on those. And so we get these notations here in the center. Okay. So if you look like alpha, that's the emission of a helium nucleus. A beta particle, we are going to just change the atomic number, but the mass number doesn't change. So the number of neutrons isn't going to change. Gamma rays, neither change. These are just a high energy photon that comes off. Positron, again, same thing. Mass number doesn't change, but my atomic number will change. Neutron, now my mass number changes, but my atomic number doesn't. And then protons, both the mass number and the atomic number will change. So we get different types of nuclear reactions. We have fission. So in fission, we're splitting a large nucleus into smaller ones, and we get a release of energy along with this. So we get this energy release because we get less than the original mass. The missing mass, it's not a whole lot, but it's converted into equations. So if you've ever seen this E equals mc squared, well, this comes into play with these nuclear fission reactions. And so we get energy, we get mass, and we get the speed of light. And so when we look at this, okay, we should get a tremendous amount of energy from a very small amount of matter as long as it's traveling at the speed of light. Now, this tremendous amount of energy doesn't matter what delivery method. So we can get a ton of energy from a power plant or a weapon, which is also why nuclear weapons are so dangerous, because there's so much energy. Okay. Our nuclear fission, it's initiated by neutrons, and so we take a neutron and we slam it at a heavy nucleus, in this case uranium. So we've got some uranium-235, okay? And then we get this metastable particle, and then we break that down into barium-141, krypton-92, and we get 3 more neutrons. Now, this is part of the danger of a fission reaction, okay? This is why they're both good and bad. Well, how did this whole thing start? Well, it started by slamming a neutron in. Okay, now what do we end up with? We end up with 3 more neutrons. So we end up with what's called a chain reaction. So we start the reaction with a neutron, and from the reaction we produce more neutrons. So the reaction keeps going and going and going. Okay, when I look at my subscripts and my superscripts, indeed, all of my mass numbers add up to 236, and all of my atomic numbers end up adding up to 92. Okay, so this is what it looks like. So I'm going to take that neutron, I'm going to slam it into my uranium-235. Now I'm going to end up with what are called daughter nuclides. That's the barium and the krypton. And that can differ. I think the previous slide I had barium-141. This is barium-140 and krypton-93 instead of krypton-92. Okay, so that can vary just a little bit, exactly what the daughter nuclide split into. But what I get is I get 3 more neutrons and I get some energy. So now those 3 neutrons are released. If I have more uranium around, boom. Now I'm going to get that chain reaction where I'm going to slam those 3 neutrons into 3 more uranium-235s. Now I'm going to get more barium, more krypton, and even more neutrons. So again, that's what we call a chain reaction. So we get 1 neutron giving us a bunch of fission products and more neutrons. So what's happening is one of the products ends up becoming a reactant for the next reaction. Okay, so we end up getting this self-sustaining reaction. Once we start it, until we do something to physically stop it, it keeps going and going and going and going. So how much energy is released? Well, we get that E equals mc squared. So if we have 1 kilogram of uranium-235, that mass of products is tiny bit less than the original. Not much, but tiny. And so we get just a little bit. Our change in mass is 1 times 10 to the negative 3 kilograms, so pretty small. Okay? But if I take that 1 times 10 to the negative 3 kilograms times the speed of light, and I keep going with it, what am I going to get? I'm going to get 9 times 10 to the 13th joules. That's equivalent to 22,000 tons of TNT. So not a lot of uranium gives a ton of energy. Now, when I look at a nuclear reactor, okay, this is basically what we have. We've got a reactor core. All right, so we are generating all this energy there. We've got this steam generator. So we get hot water, passes into that steam generator, and then that steam generator turns a turbine, which goes to a generator, which gives us electric power. All right, now, so two important factors here. So what we have in red here, we have the uranium rods. These are the fuel rods. So this is the uranium-235 that's giving us the energy. Then these gray rods we have, those are what are called control rods. So again, we have this chain reaction. Once I form those neutrons, they're going to keep bombarding more uranium until we end up with this reaction that keeps going and going and going. Well, as long as it can bounce into that uranium, this will keep happening. But I can take something with like a control rod, and I can put a control rod down in between my uranium rods to block those neutrons from hitting the next uranium rod. And so I can control the rate of my reaction there. Because again, what does the rate of the reaction? We looked at that at the beginning. Well, the number of nucleides does. So if I limit the number of nucleides by dropping the control rod and limiting access to more of them, I can control the reaction. And so this is one of the important parts of a nuclear reactor, is the ability to drop these control rods. Because without these control rods, this is where we can get an out of control reaction. So as long as those control rods are working properly, we can control our nuclear reactors really, really well. And we have a much better design for our nuclear reactors than we used to. Okay, that being said, things still happen, and we'll talk about that later. Okay, so our uranium fuel, we get this uranium oxide. It's comparable to the height, comparable in height to the diameter of a dime, so not a whole lot there. So we get these pellets, they're placed end to end and are grouped into these bundles, and we put them in there, and then we get to all of this energy. However, there's another important question too. So it's not just a matter of like what happens if we can't drop the control rods, but once we've spent the fuel rods, okay, once we're not getting any more efficient power out of them, okay, because there's only so much uranium in them, so there's only so many reactions we can do. What do we do with the spent nuclear fuel? Because there's still a little bit of residual uranium left in them. And so what do we do? Right now, a lot of times what happens is they end up getting pulled, and I think in some places, if I recall correctly, they just get stored on the roof of the nuclear facility, and they allow them to undergo natural decay until there's no more radioactive material left in them. So that is a question. What do we do with them when we're done with them? Because when we're done with them, they're not 100% spent. There's still a little bit of stuff left in them. And then how do we generate these neutrons to start it? We take plutonium, beryllium, and these alpha particles. Again, an alpha particle is a helium nucleus. This is an alpha particle. Okay. And so we're able to then get our alpha particles, and our alpha particles crashing into beryllium. We get a carbon-12. We release some gamma rays, and we get a neutron that we can start this whole chain reaction with.